on there. It'll be kind of short for chapter 20. And then, all right, so I brought me, so we could visualize some stuff here, okay? So I brought me a wire, all right? This is a big wire, and I also brought it for another demonstration too. All right, so now, if I have a wire, it creates, if the current is going this way, put my thumb along the wire like this, then I curl my fingers around, and that's the direction of the magnetic field, but it's solid all the way around, okay? So imagine this would just be solid. So I've got a magnetic field going around this wire. So at a point that's perpendicular to the table, it's coming around and it's going straight in. If the current's going the other way, if the current's going this way, then I put my thumb along the current, and then the magnetic field is curling around that way. In fact, I cross B, or actually it's V cross B, is a curl, and that's why we call it and it does curl around in that direction. Now, on the other hand, if I have a coil, all right, so this is my coil, okay, all right, and if I put what I do is I put my thumb in the direction of the coil, in the direction of the current, all right, so if the current is going this way around this coil, in other words, what is that to you all? Is that clockwise? Current's going clockwise, then I just grip it like this, and my fingers point in the direction of the magnetic field, which is going into the board. Right. So if I reverse the current, now it's doing what? It's coming out at you, right? Okay, so inside a coil, you create a magnetic field. And inside magnetic fields is where we can store different bits of energy and our information and things like that. And so that's why we have these magnetic discs and tape players that are magnetic and all that kind of stuff. All right? And so there's that. Now, what would a typical problem, in fact, this is a modification a little bit of one of your homework problems. I stole this problem from the older textbook that we used to use, but let's take a look at this. Let's take a look at this situation. All right, I got two wires. Here's one wire. Here's the other wire. Okay, now then, let's say one current is running down this way. I1 is going that way. And let's say I2 is going up this way. Okay, now then, I've got a magnetic field on wire 2. This is 1 and this is 2. Am I still in I need to zoom in. I need to zoom in here. Because this is going to require, like I said, we're going to be traveling in a foreign land now, so we need to talk slower and louder. So we'll just make it bigger. And that way, of course we'll have understanding. So I've got this magnetic field in 2 created by wire 1. So I'm going to put B21 on here. In other words, we've got this wire 1. The magnetic field is running down. So which way? So over here, as we curl around, which way is the magnetic field pointing caused by this wire over here? Out. Exactly. Good. It's coming out at you. And so this is the way we draw that. So the magnetic field looks like this. This is what B2 on 1 looks like. It's coming out at you, and that's going to equal mu naught times a current divided by 2 pi times the distance between the two. Let's say the distance between the two, d, is equal to 0.065 meters. Okay, so they're not very far apart, about 6.5 centimeters apart. All right, so that's the distance over 2 pi times 6.065 meters. Now, which I do I put in here? Do I put in I2 or I1? For the magnetic fields right here, for this magnetic field, which current are we talking? Which current created that magnetic field? I1. Very good. Okay, good. I1 created that magnetic field. Okay, now, which way is the force going? If I2 is running up, is going up. Okay, so the current is going up. So now we go to right-hand rule number 1. Right-hand rule number 2 is that curling stuff. This is right-hand rule number 1. Where we put our thumb in the direction of the current, whoa, and then our fingers in the direction of the magnetic field, which is coming out at you. So which way is the force going? That way. You just draw the force is coming out of the palm of your hand, however you orient your hand. As long as this is the thumb current, okay? This is why I changed from the book in chapter 20 a little bit. Thumb is always the current, okay? Thumb is the current, fingers are the magnetic field, so the force is going out. So now I got a force going this way. And the force on 2 caused by 1 would equal I L times B. Now I'm going to put in my subscripts here. Which current is this one? 2 or 1? 2. This one is 2. So I've got, this is current 2, but to get this guy, I had to use current 1. See that? So to get this magnetic field, I had to use current 1, but to find the force, I use current 2. All right? Makes sense. Jody's with us. Everybody's there. No, that's not true. Okay. All right. And then I gave the length. Now, on your homework problem, I think they asked for the force per unit length. Okay? You guys don't have the length here. So on your homework problem, you just basically go I2 B21. Because look what happens when I divide the length out of here. I wind up with just the force per meter, okay, which would be, then that cancels out. So for your guys' homework problem, you just cancel, you don't put in that length of the wire because they didn't give that to you. So it's just, yours will just be I2 times B21, or however you want to do it. So there's one example of a problem. Now, the way this problem would read, it would be find the force. You have 2 currents, and find the force on the second wire, or find the force on the first wire. Okay? First of all, what about let's just examine which way B1 of 2 is going here. So I've got a B1, a magnetic field on wire 1 here caused by 2. Which way would that one be going? Which way is that one going? Is it going in or out of the board? Out. Because it's being created, which current creates this magnetic field? Current 1 or current 2? Exactly. Yeah, current 2. Very good. Thank you. I was getting ready to tell you bum scoop here. All right, so that current is going up. Oh, I brought my handy dandy thing here. It also keeps your first wife away. But anyway, so put this up like this. Is that right? I've got it backwards. Don't I? No, I don't. No, I don't. Okay, so over here then, caused by this current, wait a minute. It's backwards. Yeah, smart Alec. Because if the current goes like this, yeah, it's completely backwards. Ugh. Time out. That was part of a, just to see if you were paying attention, to see if he's, oh yeah, you put that in backwards. Doesn't do any good to have a visual aid if it's backwards. All right, so here we go. Do this again. Actually, you know what we use this for? When we have kids come through on field trips, especially in nice weather, especially if they're younger. You take 2 paint sticks, do it like this, makes a great boomerang. We go outside and we fling, that's when sometimes you've seen kids out in the courtyard there. That's my doing. But anyway, all right, here we go. Now it's making sense to me. So this magnetic field is coming out at us, as we thought it would. It should come out at us. So we've got this magnetic field coming out here. And then B1 of 2 is going to equal mu naught. What is mu naught anyway? What did we call that? 4 pi times 10 to the negative 7, because we've plugged that into our TI-83s 19,000 times because mastering physics wouldn't give us the right answer no matter what we did, right? Are you running into that problem? Yeah, I apologize. I think mastering physics, they changed the problem, but they forgot to program in changing the answer. And so when you get to some of these problems, it's going to tell you over and over, no, that's wrong. And it's really frustrating. But just move on. Just say, okay, you win. And in the long run, it won't hurt you, as long as you know what you're doing. All right, but what do we call this guy? We know his value. Permeability of free space. Right. Okay, so it's the permeability of free space. It deals with magnetic fields, B fields, magnetic fields, and the permittivity of free space deals with electric fields. And we will get to, in chapter 20, I know you're excited, you're just sitting on the edge of your seat, you'll figure out that a B field can actually create, a changing B field will create an electric field. Woo! And that's how we get generators. That's how generators work. Okay, so we got B1 mu naught times some I over 2 pi times 0.065 meters. Which I is causing this B field? I1 or 2? 2. But when I actually go to find the force on 1 caused by 2, I'm going to put in I times L times B, 1 of 2. But which I is this guy now? 1. The force that he feels. Okay, now which way is that force going? He's coming out at you. The current's going down, so which way is the force going? Out that way. Right. So the force looks like this. Boink. So this guy has a force here. Here's the force 2 on 1. Here's the force 1 on 2. And you might have actually seen this before. In other words, if I had a loose wire here that's connected, it's got a voltage with a little resistor and a circuit here, and these two wires, and I turn on the switch, those two wires will go like this. They'll go boing, they'll separate. Okay? Now, what would happen if I had the currents going in the same direction? They would actually go like this. Right, exactly. Okay, good. All right, now, what would be another problem that you could possibly encounter? Since we spent 15 minutes of your life that you won't get back on this, expect something like this on your exam, okay? Because this covers everything. This covers everything, for the most part, from chapter 19. In other words, a current induces a magnetic field. Now we're going to go the other way and see how a magnetic field induces a current, all right, with chapter 20. So this would be one type of problem. And then the second type of problem you could expect from chapter 19 would be like this. Okay. I've got a coil of wire. And let's run that amperage this way. So somehow, by some kind of magic, I've got current flowing through that guy like this. And the I is all the same. And let's say I is equal to 5 amps. I is equal to 5 amps. All right. And I'm going to have this guy. Uniform B field. There's a uniform B field. That's what those things are right there. Now, I've got wire 1, wire 2, wire 3, wire 4. Okay? I want to find the forces on wire 1, the forces on wire 2, and the forces on wire 3 and 4. I want to find what forces on all of them. Is this any different than the other problem? This just got more forces, right? Oh, and each leg of this wire is the length is equal to 0.32 meters, say. Okay? And the magnetic field is 0.20 Teslas. All right? So, yeah.
You said it's just for each one part, so is that
Yeah, it's a square. It's a square. Yeah, so each one is 0.32. It would be worded much better because I would steal it actually from a textbook, so they would have it vetted, well vetted. So there we go. And all right, so here's the question. Here's the question. Does wire 1 create any force on wire 4? Not really. Not really, because once we get to the end here, there's not that much magnetic field punching down on wire 4 here at all. Okay? So what current is creating a force on wire 4 here? 3. 2. Yeah, 2. And again, since this one is going down, which way is the force going on? Which way is the magnetic field going on this wire here? Into or out of the board? Into. Right. Right. Good. It's going into because where's my? Here we go. Yes. It shows that we slide this over. It's going into, caused by this current going down. Once I got this oriented right, okay, and then this current, then the magnetic field on this guy looks like it would be going into also. Okay. So these guys, since they're opposite, they're still got forces going like this. Since these guys are going opposite, they got forces. Their forces are going like this and this. All right. And so this guy would cause a magnetic field that's going into, and this guy would cause a magnetic field that's also going into right there. And we know that the force is equal to ILB. Okay? Force is equal to ILB. And it is, and I should be a little more succinct with this, sine theta. That shows that we're doing the curl. But since the angle is what? 90 degrees with the current and the magnetic field, therefore the sine of 90 is 1. So we're good. All right? And now, and you know that B is equal to mu naught times some other I divided by 2 pi times R. Okay, or D. I think your book uses D. I've taught this so long using radius because it is a circle, so it should be radius. All right, now let's talk about mathematic induction. Okay, let's talk a little bit about mathematic. Let's talk mathematic. How about magnetic? Magnetic induction here. All right, I'm losing my mind. Okay.
Should we use R or should we use the diameter, or will we always just be given?
It's just the distance away from here, because it is a radius, really. Think about it, because this magnetic field goes in here and it's coming out over here.
Okay, so the number doesn't change. So
The number doesn't change,
Okay.
just depending on whether, but it is confusing. This R, because I did have a student one time from the old textbooks used R, and somewhere, yes, Richard. Okay, I did have a student one time, this is just a quick off-the-cuff story, kept doing these problems and he'd get them not right because he was cutting, because every time he saw R, he knew that if they gave me the distance D equals, he knew, boy, I better cut that in half because D means diameter and R means half the diameter, and so he was getting all his answers. He's off by a half, and I finally figured out what was going on. Yes, Richard?
Wires 1 and 3, do we account for the force created by magnetic field that those wires are passing through, in addition to the magnetic fields created by the other wires?
Oh, these two wires here,
Yeah.
they really don't create any magnetic field on these two wires.
No, I mean 1 and 3 will create forces on each other.
Oh, yeah, sure.
Okay, but do we have to also resolve the forces that are acting on those magnetic fields on those wires from the magnetic field that they're passing through? That you through these.
Oh, this magnetic field here?
Yeah.
Oh! That's a whole different problem. I was just making the assumption, oh, we got that thing. Yes, you would. You'd have to add those in too. Absolutely. Absolutely. So all of these, all right, so my question for you is this. Here's the question. Okay, so we've only done half this problem. Now, what about wires 2 and 4, do they experience any magnetic field at all? Or do they experience any force from this magnetic field? No. But they experience a force from this experiences one from him, and this experiences one from 4. Okay? Good. Good catch. Good catch. And that one, again, would be the force. So you'd have to take the sum of the forces, and you have to figure out which way they go. So this is a little bit harder problem. I think I'll just stick with the 2 wires and no magnetic field. Okay? There is a cool problem where if you got a circuit, you run a current through a wire that's on 2 conducting tracks and then it takes off. It's the way electric trains work, basically. It's kind of a cool little thing. But anyway, all right. So let's talk about induction. And here we go. I'm going to first show you what we're going to do now is we're going to induce a voltage. Okay? We're going to have an induced EMF. And the way this works, all right, this is one of my little demos I show the kids besides the boomerangs when they come and to class. All right, so here we go. I'm going to drop this nail down this copper pipe. Okay? I'm going to drop this nail down this copper pipe. What do you think is going to happen? Yes?
Tubing and hold itself up, basically?
Not yet. Not yet, because I don't have any magnetic material yet. This isn't, oh, okay. This isn't magnetic yet, so this is just a regular, Del Rey's a step ahead of me here. So we just go like this, bang, and it comes straight down. Now then, let's add, now I'm going to put the magnetic field on there, okay? Now I'm going to put these and I keep banging the crap out of my magnets here, but anyway, and they're chipping. But now when I put the magnets on there, it, as Del Rey said, it floats, basically, down to the bottom. And it takes a while for it to get there. Now, the first thing people do, well, the magnet sticks to the side. You all, from the time you've been playing with magnets when you're a little kid, you tried to pick you noticed that a magnet would pick up a quarter and a dime, but would it pick up a penny? No, it doesn't pick up copper. All right? Does not pick up copper. But if a magnetic field is moving through a conducting surface, all right, over a conducting surface, if we get the magnetic field to move, then it creates a current. And we've already seen that when it creates a current inside a magnetic field, what's that do? It creates a force, right? So we've got this magnetic field that's basically going this way, all right? Or it's actually kind of going like this. We've got a current that's going crossways, so that creates a force that's going up. Okay? Well, there is one going up, and there's also one, we've got the magnetic field going down, all right? And so we got the current going crossways, and so we also got one sideways. So it's like if we take this guy, if you take somebody and you drop them down a well, and they don't want to go crashing hard, so they push on the sides. That's basically what's going on. That's why it goes a little bit slower. All right? That's kind of a morbid analogy, but anyway. Not that I've dropped anyone down a well or anything in the past 3 or 4 years. But, okay. So, all right, so that's kind of the big idea of what we're getting up to. All right? So now, here we go. Here we go. And then when we get to Lenz law, that's always a lot of fun. All right, so here's our first thing. Okay, I don't know if you can read that or not, but anyway, an induced EMF. Okay, an induced EMF. What is EMF again? What does EMF stand for? Electromotive force, right? EMF stands for electromotive force. Electromotive force is measured in what? What? No. What's an EMF? Yeah, it's voltage. It's voltage. Electromotive force. Remember, voltage is what pushes charge. It's not really a force. It's not technically a force that pushes, like if I apply my hand and push this little cup of, or container of, old container of Quaker Oats, that's a real force, but this is electric motive force, but it does push charge. Pushes charge through a wire. Okay? And so you get this voltage produced in a loop or complete circuit whenever the number of magnetic field lines passing through the plane of the loop are changing with time. This is the most straightforward definition I've ever read. So, but it still probably needs some explanation, right? Say yes. It needs explanation. It does. It needs a lot of explanation. All right. Here's what they mean. Here's what they mean. Let's take this guy. So you can see, because now you can see a loop. Okay? You see a loop. All right. Now I'm going to take my magnets here. And if he was a conducting thing, and I had this, and these were like bar magnets or any kind of even these magnets work. Well, you saw it here. And I go like this, and it's changing, and it's going perpendicular to the loop. Okay? It's going through the plane of the loop. In other words, it's going through here's the plane of my loop. Right here is the circle, which is in what? We'll just call this the XY plane. It's actually the YZ plane, but that's okay. We'll call it the XY plane. And I'm pushing this guy into the Z plane. As long as it's changing, either getting stronger or still moving with time and things like that, it'll create a magnetic field, or it'll create a current in here. It produces an EMF, which, if it's a circuit, V equals IR, it will produce a current also. So that's the big idea. That's the whole enchilada of chapter 20. Now, there's several ramifications of that law. Okay, this is basically Faraday's law. All right, and now we're going to look at what the mathematics of that thing looks like. First thing we need to do is we need to come up with a thing called a magnetic flux. Now, you all worked on something called the electric flux, where we said we had the electric field times the area of that electric field equals the enclosed charge over the permittivity of free space. Y'all remember that? That's the electric flux. This one's pretty close to the same thing. It's a magnetic flux. He looks like this. And I always put a little b here so that I know we're talking about the magnetic flux of this thing. And he equals the magnetic field times the area of the magnetic field. And believe it or not, we actually create, in higher level course than this, we actually create an area vector. Okay? Which way is the area pointing? All right? In other words, the area vector of this plane right here, this has an area. We're looking at the normal to it. Y'all know what the orthonormal is to this? What would the normal be to this guy? Normal to the plane. They say normal to the plane. What is normal to the plane? Do you know what that means? It means 90 degrees to it. So anyway, in other words, something normal to it would be coming out at you, or it'd be going in. Okay? So the area of this is coming out this way, and the B is coming either out or in, or the area could be going in, times the cosine of theta. Now, because we multiply it by the cosine, since we're taking the dot product of these two vectors, it just comes out to be B times A, magnetic field times the area times the cosine of theta. Okay? B times A. And they'll either tell you what direction it's going, or they'll always tell you the direction of the B field. Okay? But we're also going to induce B fields that are going to go the other way. I'm getting ahead of myself. All right. So that's the flux. That's the magnetic flux. That's all it is. B times A times the cosine of theta. Okay? Now then, you might be going, well, how does this get us to this EMF, this voltage? All right, so here we go. Fancy E. That stands for EMF, which is a voltage. Pushes charge. So if it pushes charge and you have a closed loop, that'll create a current. Okay, so if it pushes charge, you have a closed loop, that'll create a current. So when I drop those magnets through this copper wire, there's actually a little bitty current going through, spiraling all the way through, following the magnets down. Okay, which is kind of cool. All right, so anyway, and we've actually put amp meters that are real sensitive on it, and you can see that it goes blip for a second as it passes through there, and you can actually see the amps. All right, anyway, so the voltage is equal to this. Depending on how many loops, now don't get too wrapped around the axle with this N, or this negative sign, because I haven't explained that yet, is the number of loops times the change in the flux over the change in time. Change in the flux over the change in time. Okay? Where N is the number of loops. Okay? Where N is the number of loops. That's the way you find your voltage. All right? All right. All right. Now, and this polarity, this negative sign, this guy, this has to do with the polarity of the situation. All right. So what do we mean by that? Oh boy, here we go. All right. Now now what I found is more helpful. I hope you all think this is more helpful than the slides, because I'm actually following. I've always found that the slides, when I'm going through the slides, I'm kind of like, yeah, and that slide says this, and I don't really explain what the heck is going on. I need to get this whole picture in here. Let's zoom in a little bit more. Zoom in. Probably going to cut out the whole thing I really want you to see. Oh, it's in my way. All right. Okay, this is what I want you to see. Well, let's zoom out. There we go. Now you can see it. Pretty good. You can see it pretty good. Okay, now, here we go. Got a bar magnet, and I've got this loop. Okay, and it's hooked up to this galvanometer, which means that it's a closed circuit. So it's got a circuit. So now, got the north end coming in. Now, here's my area. Here's my B field. I've got my B field, and here's the area of the loop. Okay? Is anything changing when that magnet is sitting there? Nothing's changing. Okay? So if there's this whole thing depends on things changing. There has to be a rate of change. So it's a calculus problem, really, but it's okay. We can get the big idea down and be just as well off as anybody who has to do the funky math with it. All right? So anyway, all right, so now this thing's not moving, so there's no current. Now, when I start to get this thing to move, as that magnet gets closer, what happens to the B field inside that loop? Does it increase or decrease? What happens to that B field as this magnet's getting closer to it? It increases, right? Yeah. Don't let when you're doing all this kind of hard stuff, don't let your common sense get away from you. Okay? The magnetic field is increasing. Okay? It is increasing. So here's our loop. Okay? And we're going to be here's our loop, and we're going to be bringing this magnetic field, the north end here. He's coming at you. All right? He's coming at you. Now, so I've got magnetic field shooting out this way. Guess which way the current goes? It's going to go the opposite way. Okay, so if I get a current going around this thing this way, which way is it? Now, it induces a magnetic field too. Which way is its magnetic field going to go? The opposite way. Okay, so if this thing is barging in here, increasing the magnetic field, it's going to induce a current that's going to oppose that increase. All right? In other words, it's a conservation of energy thing. All right? If it created a current that went with it, all of a sudden we'd be creating energy out of nothing. We'd be creating forces out of nothing. Can't do that. All right? Wish we could sometimes, but we can't. All right? That happened once 14 billion years ago, and ever since then we've been trying to figure it out. But anyway, all right, so it's coming in. So this creates a magnetic, so if this was creating a magnetic field coming out at you, it creates a current going against you, and that's Lenz's law. That's why that negative sign is in the thing. Long way to go to find out why that negative sign is there, but that's why. All right, so now look what happens. When we start to pull this magnet away, what happens? Is the magnetic field increasing or decreasing here? Decreasing. And so the wire goes, hey, wait a minute. The party is just getting started. Come back. All right? In other words, it's going to create a current that's going to try and help it when it's decreasing, it tries to create a current that says, hey, come back. Why does it come back? All right? But when the magnetic field is increasing, it creates one in the opposite direction. So no matter what happens, if the magnetic field is decreasing, it'll create a magnetic field so it'll help it try and increase. And if it's decreasing, it'll create one that's trying to make it decrease. Okay. All right. So basically, what happens is, if the magnetic field is moving towards it, it's going to create a current that's going to create a magnetic field that's going away in the opposite direction. If the magnetic field is decreasing, then it's going to create a current to try and increase it to come back. All right? So that's Lenz's law, and that's very difficult to get your head around. It was for me. All right? It was for me. Maybe. All right. So here's Lenz's law. Here's actually what it says. And this is in your book. And it says, Lenz's law says this: an induced EMF in a wire loop or coil has direction such that the current it creates produces its own magnetic field that opposes the change in the magnetic flux. That's a much better way of saying it. Okay? Through that loop or coil. All right? All right. So now, let's see how well we understand this. Here we go. This is one of my favorite things. This is one of my favorite little exercises. Okay. There's my uniform magnetic field. Which way is it going? My uniform magnetic field. Which way is it going? Into the board. So I got a B field going into the board. All right, now what I'm going to do, here's what I'm going to do. I'm going to drop this ring, this conducting ring right here. He's outside of here. All right, and let's say I've got a little string attached to him or something. And I'm just going to pull him through here at a nice constant velocity. All right, so he's going to start a velocity right here. This is situation A. Right here at situation A, is there any current at all going through that coil? Is there any current there? No, why not? It's as easy as you think it is. Because he's not in a magnetic field. He's not moving through a magnetic field, so therefore his flux can't be changing. All right? So now, let's look at situation B. All right? Here, he's moving in. And notice, okay, now he's moving in and he's going to be coming through. Now what's happening to the presence of the magnetic field inside that loop? Is it increasing or decreasing? As it's moving, he's moving this way. I'm sorry. He's moving this way. All right, so he's moving down. So what's happening? Is it increasing or decreasing? You already said it. Increasing. So what is he going to do? What direction is the current that he's going to create? What kind of magnetic field does he want to create if this is if it's increasing going in? What's he going to do? Create one that's going out. So if he creates one that's going out, which way is the current going? It's going counterclockwise. It's going. Yeah. I've got to do it this way. I'm sorry. I got to do it this way. There we go. It's going like that, counterclockwise. Okay? Because if I put this here, magnetic field coming in, yeah, it's going nice and counterclockwise. Magnetic field's going in, so he's going to want to create a current that's looping around. It's going out. Okay, so now, so that's a counterclockwise current. All right? Now then, situation C. He's completely inside there, moving along. He's completely, I drew that in a kind of a hurry. He's completely inside there. What's going on with his current? Is there any? Maria says no. Why does Maria say no? Why would she say no? There's no changing magnetic field. In other words, the flux isn't changing. My BA cosine theta is not changing. My magnetic flux is not changing. So therefore, I equals 0. I equals 0 on that one too. Okay. Last but not least, and then I'm going to let you go, because once you get this idea, then the rest of the chapter just flies by on Friday. We'll just zip, de-doo-dah through the whole thing. Okay, D. We'll even learn about transformers a little bit on Monday, and then we'll review for the exam. Okay. Oh, and by the way, while I'm thinking about it, I'm changing the exam again. I always do that. There will be 15 to 20, no more multiple choice, but it will be short answer type things. In other words, you'll describe something like this, or something. Okay, I'll say if this is a situation, the question might be, if this is a situation, which way is the current going? And you'll say, oh, it'll be going counterclockwise because it'll want to oppose the magnetic field, change the magnetic, those kinds of things, because I think I've done this all to you before, because what happens on a multiple choice exam is, especially when the material's new to you and you've studied it hard, you'll know what the right answer is, and they'll put the right answer but in a wrong context. And you'll pick that one, and they did that to you on purpose so you'd get it wrong. That's not fair. That doesn't test what you know, that tests how well you can take a test, basically. All right, so I want to go, and they have some nice short answer type questions, so that's what we'll ask, because it's like the old, I think I've done this trick to you before. If you all ever done where you spell shop out loud, if you all ever done that, go ahead, try it. Spell the word shop. Try it one more time. What do you do when you come to a green light? No, you don't. That's what multiple choice tests do to you. Okay? There's my golden example of a multiple choice test. You know good and well you don't stop at a green light. But your brain was already activated with the whole OP thing. So anyway, OPP. Anyways, all right. So now, last but not least, and then I'll let you go. Bless your hearts. Okay, here we go. Got this. Okay, and, there is a magnetic field in here, but at this juncture, what's happening to this magnetic field? Is it increasing or decreasing? Decreasing. So what kind of magnetic field will the current want to induce? Clockwise. Why? Because it wants to help it, right? It's going to try and create a current that's going to try and help this, so it's going to go, oh, good, cool, clockwise. There. Oh, no, that doesn't work. Here. So that'll go clockwise. All right. Okay, real quick, remember the flux is BA times the cosine of theta, all right, and the EMF is equal to the number of loops times the changing flux changing with time. There you go. There's chapter 20. You're done. You got it all.